the parts per million and parts per billion is another very common concentration unit used especially when looking at small concentrations of what may be contaminants in water. And for example, but I need to tell you something. We did look at ppm and ppb when we were talking about air. And in the context of air, ppm and ppb refer to the number of selected components, whatever it is, of air per million or billion, if it was ppm or ppb, number of total air particles. And the particle in that case was an atom, a molecule, or an ion. For example, when we said, there might be 385 parts per million carbon dioxide in the air in some particular location. What that meant was that there was 385 molecules. That would be the particle of carbon dioxide. It's called a molecule of carbon dioxide in 1 million molecules of the mixture. Okay, and in this case the mixture was air. All right, so in that case, in the case of gases, which air, parts per million and parts per billion refer to selected component in the term of the particle, whatever that particle may be, an atom, a molecule, or an ion. In aqueous solutions, we have a slightly different interpretation of parts per million and parts per billion, and that's important to recognize. We still call it parts per million and we still call it parts per billion, but the meaning in this case is the part is the gram, not the individual atom, molecule, or ion, but the gram of selected solute per million or billion grams of solution. Okay, so when we're talking about parts here, we're talking about the mass. When we're talking about parts here, we're talking about the individuals. All right, just something to keep in mind. So for example, if we said there's 66 parts per million calcium ion in water, what that means is that there's 66 grams of calcium ion per million grams of the water. Okay, and in reality we should say per million grams of the solution, but in these very, very low concentrations, parts per million, parts per billion, we approximate the solution to be the amount of water because it's mostly the water, and so it just makes moving around with the calculations easier. So the approximation, instead of saying the solution, which would be the calcium plus the water, we just say the water. And there's an analogous for parts per billion. If we had parts per billion, it would be 66 grams of calcium per billion grams of water. Okay, so it's a different interpretation. Instead of particles, we're looking at grams. That's important to remember when we're doing these types of problems, which I'll show you right here. In this, let's just practice this unit conversion here. It says, part A, 80 micrograms of lead were detected in 5 liters of water. What is the concentration of lead? Express your answer in both parts per million and parts per billion. Okay, so we're given some concentration, all right, but the concentration unit that we are given here is really in terms of micrograms per liter. If you say we have 80 micrograms of lead, and lead of course would be in the form of the ion, in water, in 5 liters of water. Okay, that's what we know about this particular mixture. And we want to express that amount of lead and that amount of water in terms of parts per million and parts per billion. Okay, so what we're going to have to do is remember the interpretation here. Parts per million means, I'm going to put it right here, parts per million means grams, in this case it would be grams of lead per 1 million grams of water, and that would be parts per million, and parts per billion would be grams of lead ion per 1 billion grams of water. Okay, so we want to go from micrograms per liter to these units. How are we going to do it? Well, we're going to just convert both of these units to, we're going to convert this to units of grams and we're going to convert the liters to units of billion or a million grams first. Okay, so first of all, so this is what we're given. Okay, and this is what's wanted. We want to express it in this way. Okay, so what you can do is just take your time, think about the conversion path for each of these units, the unit in the denominator and the unit in the numerator. For the numerator, the conversion path is going to be from micrograms to grams. That's easy enough. The conversion factor that we need there is just the definition of a microgram, which is 1 microgram is equal to 1 times 10 to the -6 grams. That's the definition. But I'm going to have to, I should have written it the other way, because I'm going to be converting from micrograms to grams. My bad. So let's write it the way we should write it. 1 times 10 to the -6 grams per every 1 microgram. Just going on the metric definition there. Okay, that's the conversion factor I'm going to use for that particular conversion. For the liters to billion grams of water, what I'm going to do is I'm going to convert from liters to milliliters. And then I'm going to recognize to get from volume to mass of water, the conversion factor that I need is the density. And the density of water is 1 gram per 1 milliliter. So then I know using that conversion factor I can get to units of grams. And then to get to the unit million grams, again I'm just going to use the definition that million equals 1 times 10 to the 6th. Okay, so there's 1 million grams in 1 times 10 to the 6 grams. Okay, and that's how I'm going to get to units of million grams. Alright, so I can just put this all together and do it in one conversion sequence. So you always start with what's given, 80 micrograms of lead ion per 5 liters of water. That's what our concentration is in the given units, in the given amounts. So first I'll do the easy one, convert from micrograms to grams. 1 microgram is equal to 1 times 10 to the -6 grams. Alright, that is of lead ion. So now I'm in the correct units there, so this unit is going to cancel. Now I'm going to work on my denominator. 5 liters, I need to get to milliliters. There are 1,000 milliliters in 1 liter of water. Okay, and then so my, oh my goodness, that's upside down. Oh gee whiz. Okay, here let's, my goodness, 1,000 milliliters. Okay, so the liter unit's going to cancel. All right, now we're in units of grams per 1,000 milliliters. Now I can convert from milliliters to grams because the density of water, 1 milliliter equals 1 gram of water. Okay, and then now I'm in units of grams of water, and I need to get to billion grams of water, or million grams of water. So 1 million grams of water is the same as 1 times 10 to the 6 grams of water. Okay, so now if I just do the math, 80 divided by 5 times 1 times 10 to the -6 divided by 1,000 times 1 times 10 to the 6th, I end up with 0.016 parts per million. So that's the concentration in units of parts per million. If I want to convert to parts per billion, I do the exact same thing, except for when I get down to this last step, I'm going to convert to billion, and it's going to be 1 times 10 to the 9th grams of water. So everything is the same, ditto all the way down to the last step, and that's going to be the same as 1 billion grams of water. And when I do the math there, I'm going to end up with 16 parts per billion. Okay, so this is how we interpret parts per million and parts per billion in terms of aqueous concentrations, and how we convert a given mass and volume to the parts per million and parts per billion. And you'll see these types of water contaminants expressed in terms of milligrams per liter, micrograms per liter, parts per million or parts per billion. It just depends on the chart and the data and who's preparing it for you. Okay, then the next part of the question is the maximum lead concentration of drinking water allowed by the federal government is 15 parts per billion. Would the sample in Part A be in compliance with federal limits? Well, when we look at the parts per billion, we are above the acceptable limit of 15. So the answer there is no, and the reason why is because we are above the limit. Okay.